Welcome back to our series on AI and machine learning. In this lesson, we'll delve into deep learning, an exciting and powerful subset of machine learning that has revolutionized many fields. We'll cover the definition of deep learning, the basics of neural networks, and two specialized types of neural networks: convolutional neural networks, CNNs, and recurrent neural networks, RNNs. Let's start with the definition of deep learning. Deep learning is a class of machine learning that uses neural networks with many layers, also known as deep networks. These deep networks are capable of automatically learning features and representations from data, making them incredibly effective for complex tasks such as image recognition, natural language processing, and more. The term deep refers to the number of layers in the neural network. The deeper the network, the more layers it has. At the core of deep learning are neural networks. A neural network is composed of layers of interconnected nodes, or neurons, which are designed to mimic the way the human brain processes information. The basic structure includes an input layer, one or more hidden layers, and an output layer. Each neuron receives input, processes it using an activation function, and passes the output to the next layer. Activation functions introduce non-linearity into the network, enabling it to learn complex patterns. Common activation functions include the sigmoid function, TANH, and the rectified linear unit, ReLU. Now, let's discuss convolutional neural networks, or CNNs. CNNs are specialized neural networks designed for image processing tasks. They are particularly effective at recognizing spatial hierarchies in images, such as edges, textures, and shapes. CNNs consist of convolutional layers, pooling layers, and fully connected layers. Convolutional layers apply filters to the input image to create feature maps, highlighting important features like edges and textures. Pooling layers reduce the dimensionality of these feature maps, making the network more efficient and reducing the risk of overfitting. Finally, fully connected layers interpret the extracted features to make a final prediction, such as identifying the objects in an image. For example, a CNN might be used in a self-driving car to process images from cameras and identify pedestrians, other vehicles, and road signs. The convolutional layers detect features like the outlines of objects. The pooling layers simplify these features, and the fully connected layers classify the objects to help the car navigate safely. Next, we have recurrent neural networks, or RNNs. RNNs are specialized for sequence data, such as time series or language. Unlike traditional neural networks, RNNs have connections that loop back on themselves, allowing them to maintain a memory of previous inputs. This makes them well-suited for tasks where context and sequential information are important. Each neuron in an RNN not only receives input from the previous layer, but also from its own previous state, enabling it to process sequences of data. For example, RNNs are used in natural language processing tasks like language translation and sentiment analysis. In language translation, an RNN can read a sentence in one language, maintaining context from each word, and generate the translated sentence in another language. In sentiment analysis, an RNN can analyze the sequence of words in a sentence to determine whether the sentiment is positive, negative, or neutral. To summarize, deep learning is a powerful class of machine learning that uses neural networks with many layers to automatically learn features and representations from data. Neural networks consist of neurons, layers, and activation functions that process input data. Convolutional neural networks, CNNs, are specialized for image processing tasks, while recurrent neural networks, RNNs, are designed for sequence data, such as time series or language. In conclusion, understanding these fundamental concepts and specialized networks is crucial for leveraging the full potential of deep learning. Each type of neural network has its unique strengths and applications, making them valuable tools in the data scientist's toolkit. In our next lesson, we'll explore practical applications and case studies of machine learning in various industries. Stay tuned.